Hello, everybody. This is Mark. I thought I'd go through the Arduino oscilloscope program that I've kind of written and scribbled out. I assume that you've also got a copy. If you've got a copy of the program, there's also a manual that goes with it. It's about 25 pages long. Explains things in a lot finer detail that I'm going to cover here. I'm just trying to get a really quick rundown with it. Let me go to this. Okay, so here's the program itself. It's long. It's a little less than 2,000 lines. It's kind of messy in there. There is a description in the manual about how some of this works if you're really curious. It does very. There's only one subroutine that actually uses the Arduino libraries. Everything else is actually handled manually. It's instead of setup and loop, it does main. But this will compile pretty normally on any of the more recent versions of the Arduino development environment. Again, it must run on an ATmega 328P processor running at 16 megahertz. So nothing fancy there. We tried to make this as cheap as possible. We're running on Arduino Nanos, which are really... this is a Nano. It's the cheapest one you can get. We sell these in the EE shop for $6, I think, including the cable. You can get them even cheaper on Amazon if you buy a few of them. I think I spent $14 and got 3 of them with the cables. So they are built cheap. They may break. It's like, okay, fine. You throw them away and grab another one. I like the Nano versus the Unos because you can plug them directly into the prototype boards, which makes it way easier to work with. So just to get there quickly. Okay, so if I go to development environment and let's see here, we want it's the Nano, it's the 328P, it's on the right port. So if I say upload, compiles, writing, verifying. Okay, done. So going back to the display for a moment, you can see the light is the light that's near the bottom of the 4 is blinking fast. It's actually blinking slightly less than 10 hertz. So it's when it's doing that, it's actually running the A to D converters and it's sampling 10,000 times a second on 2 separate channels. So it's actually doing 20,000 A to D converters per second. We had to reduce the resolution of the A to D conversions for a couple of reasons. One is you can't run it that fast if you go for 10 bits of resolution. And the other one is we don't have any memory left. The chip only has 2048 bytes of memory. And we have a depth of 512 samples for both of those channels. So 8 bits, 512 times 2, that's 2048 right there. That's half of the memory in the system. For the buffers. I'll let you work out some of those details. They're just 2 input pins as our inputs for the scope. So and then as we power up the program, it actually defaults. There's 3 clock outputs that crank right along, and clock C is already set up to be an output. It's giving a pulse that's 9 milliseconds in length once a second. So if I just connect, I know that the clock output comes out on the D12 line. These are all listed in the manual, so I'm not going to go over all the details. You can do that. I'm going to take this and connect it to the A1 line. The scope inputs are A0 and A1. That'll at least give us something we can look at for a display. So let me go back to this. We need to bring up the actual serial plotter. And down here, when you bring this up, it's a blank screen. It's 115,200 baud rate. You can select, that's the one it has to be. If it's not set at that, you can correct it. We need to change this to carriage return over here. And then if I push send, that shows us that we're running okay. Again, we're getting a 9 millisecond pulse that occurs once a second. The triggers are also set up. It's actually watching the clock line itself, so it'll trigger automatically even if you don't have a trace on or have that jumper on there. You'll notice that the that there's two traces right there. The second trace is caused by a floating input on the A0 line. And if I just take another jumper, we can get rid of that. I can just take a jumper from A0 line and just take it to ground. And let me go back. And then, so that gets rid of the extra trace. Okay, so here's our 9 millisecond pulse. We're running as fast as we can run. There's 5 divisions on the display. We're doing 500 samples across the display. So each division is going to be 10 milliseconds. So we're slightly less than 10 milliseconds. We said it was 9. That comes out about right. So, okay, so I've got a 9 millisecond pulse there. We want to look at an analog signal to make it a little bit more interesting. So if I take, let me add a resistor and capacitor to this thing. Let me go back to this. Okay, now I'm going to just take another wire off that same clock pulse, and I'm going to bring it out here a little bit farther so I can actually reach on it. And then I'm going to put in a 10K resistor. I think that this is what we do in the manual also. 10K resistor. And then I'm going to take, you'll notice I've got a wire to ground here already. And so I'm going to put a capacitor between here and on the other side of the resistor to ground. And then I'm going to take this line that went to A0, which we grounded, and I'm actually going to put it on top of the voltage for the capacitor, like there. And then let me go back to the other display. Okay, so now when I say refresh, now we get to see both traces at once, so the advantage of seeing the dual trace concept of this. This is the charge and discharge curves of the capacitor. So when that pulse goes high, this is standard charge curve. Goes back low, it comes back down. Now, the trigger right now is set at falling with the source of being number 8. Number 8 is clock C, which if I look up here on the top line, that's CC. It's got a duration of, or the dividing factor is 100 microseconds. The period is 10,000 cycles. Well, 10,000 times 100 microseconds is going to be the 1 second. And then it's going to be high for 90 clicks of that. Well, the 90 clicks of that is going to be 9 milliseconds. So I can change this to make it longer because I want this pulse to be higher so it charges longer. Now, it's actually triggering on the falling edge of this. So this falling edge is going to stay the same, but the rising edge is going to go off to the side. So instead of 9, let's make it, let me make it 30, or 30 milliseconds. So I need to put 300. So I want clock C, I want it to be high for 30 milliseconds, or 300 of those 100 microsecond pulses. Okay. So that updated the line on the top. Now I hit one more return, and then we get that. Now we can see that we're charging up much higher. And if I want to see how long that pulse actually is, I can change that trigger from triggering as it falls to triggering as it rises. So I can just type in TR, say I want to trigger on rising, and then hit another return to make it redraw it. And this so you can see how long the pulse actually is. So you can see that it runs for an entire 3 divisions there, which is going to get us our 30 milliseconds. Okay, let me go back to trigger falling. Now, I actually want to, if I want to time between 2 points, like if I'm trying to estimate the value of the capacitor itself, I've got a 10K resistor, I've got a 1 mic cap, but capacitors, the tolerance on those is really quite high. So I actually want to, in those, the numbers on the left edge of the screen, it goes up to, 6,000's clear at the top. The 4,500 right there, those are actually millivolts. Well, all those lines at the top, that has to do with some other stuff. But I mean, that's actually millivolts. And we can actually calibrate that with the V command and we actually put in the number of millivolts for 5 volts. Remember, if it's 5.1 volts, you've got to put in, you would type in V5100 and hit return, and that would be fine. But I can set trigger levels also, and I could say I want to trigger on whichever source I want. So I'm going to say I want to trigger on source 0, which is now triggering on the actual analog 0 input, which is the one that the capacitor is on. So if I hit another return, we could see on that status line at the top, it says TF underscore S0 underscore L2500. Okay, so it's saying we're triggering on the falling edge of S0, which in the manual will tell you that that's the analog channel 0. And we're at a level of 2500. Well, the level of 2500 is 2.5 volts. Now, when I told it to redraw, it added this extra line in here, and that's right at, 2.5 volts. Well, I want to move that clear up to the right up here at the 4.5 volt level. So I want to say trigger level 4500. Okay, and now you can see that it's, and I hit an extra return to make it redraw. It hit that line, moved it all the way up there. Now, I also want to measure until it hits a specific point in terms of how long it takes, so I can figure out how long it takes to drop to a specific voltage. Okay, that's 4,500. Let's set a measurement level. And right now, and we also want to see it as it falls. So I'm going to say I want the measurement, that's an M, an L, saying I want it the level, and I'm going to put 500 because I want 5 volts in there. Okay, I can't see anything yet. It just says MX up there. Well, I didn't actually turn it on yet. So I could turn that on by saying I want it falling. So MF for falling. Now you can see what it says up there. It changed the status line. It now says MF S0, which is the analog channel 0. The level is 0500, which is our half volt. It's all in millivolts. And let me hit one more return so it actually redraws things for us. Now you can see it's drawn an extra line at the half volt. And if you look at that line, it says, at the status line again, it says the second item in is MF, saying measurement on the falling, S0, analog 0, level 0500 for half volt. Now, and you can see that it's got this T0.0236. Now that number will be different on yours because it depends on the capacitor and the resistor. But that's how long it took to get from the trigger point of dropping through 4.5 to a half a volt. Now I can do the calculation really quick. I'm not going to do it on the video here. And estimate what the capacitor is if I know what the resistor is. Well, most meters will tell you the resistance. If I just assume 10K, then it'll be fine. And even if you're not really well calibrated with the voltage, that drops out of the equation either, because the first thing you do is you divide the 0.5 by 4.5. That'll give you how much percentage you dropped, and that's equal to the e to the minus t over RC. Okay, so you can just work all that out backwards, and it'll give you that. But that allows you to make measurements. The other thing you want to notice on this is if you're curious as to where something triggered, you'll notice that the fifth line from the top, it's got a little spike that goes up right here on the trigger point, and that is where this line, the channel A0 dropped through the 4.5 point, and then there's a smaller tick that's up that's clear over here, and that matches where this line crosses over here. So that's the 2 points that we're timing between. We could change our voltage at any point. We could say we want a measurement level to 1 volt. And I hit the return twice so I can get it to move. And you can see that it's shifted it quite a bit over to here. Our timing is now, it took less, it's now 0.0158 seconds to drop from the one to the other. So we can make some timing adjustments right here. Let's see, what else can we do with this? I think that's enough for the moment. Just a really quick how to make a measurement and get something off the AOScope program.